Okay, for this part we we pay attention to the complex numbers. First of all, we need to go back to remind ourselves the set theory. So what numbers do we have? We have the natural numbers, okay, 0, 1, 2, 3, 4, etc. We have the integers z. We have the rational numbers q. We have the real numbers r. Here we have the set of irrational numbers and the set of complex numbers c, which contains all the other numbers. So we can write that n is subset of z, subset of q, subset of r, and r is subset of c. Okay, how did the complex numbers arise? So we had x squared plus 1 equal to 0. We have this equation, right? So here we know that we cannot find a solution for real numbers. Let's see this one, x squared equal minus 1. But as we know, in the set of real numbers, we cannot solve this equation. However, let's take x to be the square root of minus 1. And let's call this I. Then I squared equals square root of minus 1 to the power of 2 equals minus 1. So the set of complex numbers can be written in the following way. X, y are the real numbers such that z equals x plus iy, where I is the square root of minus 1. So any complex number can be written in this form: real part of z plus I imaginary part of z. For example, z equals 1 plus 3i. The real part of z equals 1. The imaginary part of z equals 3. The conjugate complex number we denote by z bar equals 1 plus 3i bar is 1 minus 3i, is the real part of z minus I, the imaginary part of z. So the conjugate has the imaginary parts have opposite sign if it is conjugate. So z equals real z plus I imaginary part of z. Z conjugate equals the real part is the same minus I, the imaginary of z. Okay. How can we represent here? We can represent the complex numbers in the complex plane. This is the real part of z, imaginary part of z. So let's have a look at the complex number z equals 1 plus 3i. So the real part is 1, the imaginary part is 3. That's the image of the complex number. For the conjugate, z bar equals 1 minus 3i. So the real part is the same, the imaginary part is minus 3. So it's m z bar. Okay. How do we calculate the modulus of z? Is the square root of the real part of z squared plus the imaginary part of z squared. So let's say that we want to find the modulus of this complex number is 1 squared plus 3 squared. 1 plus 9 equals 10. So the modulus z equals the square root of 10. That's the length. That's the distance here from the center of the complex plane. So the length z equals the square root of 10. Let's say that we have w equals 2 minus 3i. The modulus of w equals the square root, the real part squared, plus the imaginary part, which is minus 3 squared. And this is 2 squared plus 3 squared. Yeah, this is 4 plus 9 square root of 13. So the modulus of W is the square root of 13. Okay, now let's try to find in all these cases what is the modulus of the complex number. Here the modulus is the square root of 1 squared plus 5 squared. 1 plus 25 is the square root of 26. The modulus of this complex number is the square root of 3 squared plus 2 squared. 9 plus 4 square root of 13. The modulus of this complex number is 4 squared plus 3 squared. 16 add 9 equals square root of 25, so that's a 5. And here the modulus of z is the square root of 4 squared plus minus 3 squared. So we have the square root of 4 squared plus 3 squared. That's 16 plus 9, square root of 25, and that gives me 5. Okay. So this is the calculation of the modulus of z. Now the other part is a polar form of a complex number. So the z equals x plus iy, this is the Cartesian form, Cartesian or rectangular form. If we want to convert into polar form, z equal r times e to the power of I theta, or we write r angle theta. R is the square root of the real part of z squared plus the imaginary part of z squared, and theta is the arc tangent of the imaginary part of z over the real part of z. Let's have a look at some examples. Let's have a look at these examples here. Okay, the first one is z equals 4 plus 4i. So the modulus of this complex number is 4 squared plus 4 squared, square root 2, so it's 16 at 16, 32, square root of 32, okay? Now if we want to find the angle theta is the arc tangent of the imaginary part, which is 4, divided by the real part, which is 4. Arc tangent of 1. Here you can put this on a calculator and you get 45 degrees. So we can write z equals r e to the power of I theta, square root of 32 times e to the power of I 45 degrees. E to the power of I theta equals cos theta plus I sin theta, and this is the Euler's formula. Or we can write square root of 32 angle 45 degrees. The second one, z equals 5 plus 5i. The modulus of z equals 5 squared plus 5 squared. The square root of this is square root of 50, that's 25 here, and this is 25, and this is my r, the radius, and then I take theta equals arc tangent, the imaginary part, which is 5, divided by the real part, which is 5, so it's arc tangent of 1, 45 degrees. So this should give me z equals square root of 50 e to the power of I 45 degrees. Let's have a look at the third one. Z equals 6 plus 6i. The modulus of z equals square root of 6 squared plus 6 squared, so it's 36 plus 36 square root of 72. And theta is the arctangent of the imaginary part divided by the real part, arctangent of 1, and this is 45 degrees. So I can write z equals square root of 72 e to the power of I 45 degrees. Okay. Now, how do we solve complex polynomial equations? Let's say that we have z to the power of n equals b here. Z to some power n equals b. Z k equals b to the power of 1 over n times e to the power I 2k pi plus theta divided by n, where k equals 0, 1, 2, etc. So what does this mean? Let's have a look at an example. Z to the power of 6 equals 1, okay? Here n is equal to 6, so in order to find the root, zk is, this is b equals 1, 1 to the power of 1 over 6, we use the formula here, this one, e to the power of I 2k pi plus theta is the arctangent of 0 over 1, because here the imaginary part is 0. So the angle theta is equal to 0 divided by n. N is equal to 6. Zk equals, this is 1, so it's e to the power I 2k pi over 6, and with this is e to the power I k pi over 3. So we have to calculate 6 root. Z0 is e to the power of I 0 pi over 3. Z1 equals e to the power of I pi over 3. Z2 equals e to the power I 2 pi over 3. Z3 3 pi over 3, so it's e to the I pi. Z4 e to the I 4 pi over 3. Z5, how many roots? We need to have 6 roots in total, yeah, so we have here the k goes from 0 to 5. If we have 6 root, the k goes from 0 to 5, e to the power of I 5p over 3. That's my roots here, and here, using this identity, I can put them back, using this identity here, Euler's formula, I can put them back into rectangular form. So I can write here cos pi over 3 plus I sine pi over 3. Cos 0 plus I sine 0, sorry. Cos pi over 3 plus I sine pi over 3. Cos 2 pi over 3 plus I sine 2 pi over 3. Cos pi plus I sine pi. Cos 4 pi over 3 plus I sine 4 pi over 3. And here cos 5 pi over 3 plus I sine 5 pi over 3. Now let's go to the other part, loci of complex numbers. We have z minus z naught less than r. What does this mean? We put z equals x plus iy and z naught equals x naught plus I y naught. We substitute here z minus z naught less than r is positive, x plus iy minus x naught plus I y naught less than r, x plus iy minus x naught minus I y naught is less than r. I split the real part, x minus x naught plus I y minus y naught less than r, and this is the square root of x minus x naught squared plus y minus y naught squared less than r. I can raise to the power of 2. So what is this? If we have x minus x naught squared plus y minus y naught squared equals to r squared, then we have a circle centered at x naught y naught with a radius r. If it's less than r, it means that in this circle I take only the parts that are inside the circle. I take the complex numbers that lie inside the circle. Let's have a look at an example. I have this here, z minus 3 plus 2i less than 7. Z minus 3 minus 2i is less than 7. I put z equals x plus iy. Minus 3 minus 2i is less than 7. I split x minus 3 plus I y minus 2 is less than 7. And what I get, x minus 3 squared plus y minus 2 squared is less than 7 squared. So I have a circle centered at these points, x naught equals 3, y naught equals 2. The center of the circle is here. And the radius is equal to 7. So I want all the points that are inside the circle. This is what is the loci of complex numbers. I want only the complex numbers that lie inside this circle.